Today we're going to talk about the modern view of the structure of the atom. We're going to talk about the three subatomic particles that are most often involved with chemical reactions. And of course, we're going to dive a little bit into calculation of average atomic mass, that number that you see at the bottom of the periodic table, or of each cell on the periodic table for each element. So let's dive right in. First off, the reading that goes along with this. Reading is going to be section 2.1 in your textbook through 2.4. There will be some stuff covered in 2.1 and 2.2 that was covered in general chemistry, Dalton's theory, and we'll also be taking a look at the experiments that led us to the modern view of the atom. I'm not going to lecture on those today. You're going to be responsible for reading 2.1 and 2.2. I'll be lecturing mostly on 2.3 and 2.4 for this lecture. So we're going to dive right into 2.3, which is our modern view of the atom. Okay, and so let's dive right in there. Now, if we take a look at any cell on the periodic table that has an element in it, we'll take fluorine as an example. We notice that we have some other information given to us, and we remember this from general chemistry, hopefully. We have a couple different things. First off, we're going to make the assumption right now, and this will not hold true always, definitely soon it won't hold true, that this fluorine atom is neutral. Now, what that means is we're going to have equal numbers of protons, which are positively charged particles, and we're going to have equal numbers of electrons, which are negatively charged particles. And if you remember from general chemistry, those electrons can be either shared, but they can also be transferred out or transferred in chemical reactions and causing ionic bonds. So we'll be talking about that very soon. So let's dive right in here. So of course, we remember general chemistry, this top number here, this 9 is going to be our atomic number, and that's going to be equal to the number of protons in this atom. And if the assumption is that this atom is neutral, then that is also equal to the number of electrons. So we would say that fluorine has 9 protons and it also has 9 electrons as long as it's neutral. This number down here, we give it a couple different names. Call it the mass number or average atomic mass, which we'll be talking about later on. This is going to be the value that is equal to the number of protons plus the number of neutrons. So if we ever have to calculate the number of neutrons, we know that the atomic number is equal to the number of protons, and if the mass number is equal to the number of protons plus the neutrons, we just subtract. So in the case of fluorine, we would take 19 minus 9, and that would give us 10 neutrons. So neutrally charged particles. So we would say that fluorine has 9 protons, 9 electrons, and 10 neutrons in a neutral atom of fluorine. We should also talk about isotope notation. We'll talk about what an isotope is here in a couple minutes, though. But isotope notation is just another way to write what we see on the periodic table. So if we were talking about this particular isotope that is in front of us, we would say that this is fluorine 19. Obviously, the 19 is the average atomic mass, or the mass number. As long as we write fluorine, we know it's always going to have 9 protons, because fluorine, if you change the number of protons, you change who the atom is. So that's one way fluorine 19 can be written. We can also write it this way. Sometimes it's written as fluorine 19 like that. And you may remember that from when we did nuclear chemistry in general chemistry. We often use this type of isotope notation. Sometimes they'll leave off the 9, other times they'll put in the 9. Really depends. It's useful in nuclear chem to include it, but it's not necessarily always included. So just keep in mind that as long as we have the symbol of the element, we know the number of protons, or if we know the number of protons, we have the symbol. But what that does tell us is that if we do have an isotope, we can have the same atom, which is going to be the same number of protons, or same element. Remember, if we change the number of protons, we change the element. But we have a different number of neutrons, and that's going to affect the average atomic mass of that element. Adding neutrons is going to make it heavier, as the neutrons take up about roughly half of the mass of an atom. Give you an example of isotope notation given this. So let's say we have carbon 12 and also carbon 14. Carbon 12 is the most common isotope of carbon, makes up about 99% of carbon found on Earth. Carbon 14 is an important isotope in carbon because it's used for radioactive carbon dating. It decays at a very regular rate, so they can use it. Scientists use carbon 14 to figure out the age of a very old specimen that used to be alive. We're always taking up carbon 14 into our bodies, and then it decays at a regular rate. So these would be two isotopes of carbon. Notice that they both have the same symbol. That's a tip-off, it's an isotope. If we calculated the number of protons, they would both have the same number of protons. Because they're carbon, they're going to have 6 protons. I didn't say anything about whether or not they have lost or gained electrons, so let's assume they're neutral and say we both have 6 electrons. But in the calculation of the number of neutrons, that's when things are going to change. This is going to have 6 neutrons, as we would take the 12, which is the mass number, and subtract it from the atomic number of 6, but this one would have 8 neutrons, and that's what makes them isotopes of each other, even though they are the same atom. If we threw, let's say nitrogen into this mix, nitrogen would not be an isotope of carbon, even if it had the same number of, let's say, electrons or the same number of neutrons. It would, because it's nitrogen, it has 7 protons and not 6 protons, which does not make it an isotope. Okay, we're going to talk next about average atomic mass calculations, and let's talk about a couple terms that'll pop up here and there. Okay, so the first thing is atomic mass unit we're going to hear used, which has the abbreviation of AMU, and 12 AMUs is going to be assigned to the isotope of carbon 12, an arbitrary number. But because atoms' atomic mass are so small, it becomes easier to use larger numbers like this. And so let's take a look at what an average atomic mass calculation looks like and some of the ideas behind it. So first off, the weighted average of percent abundance of isotopes of an element is how we calculate average atomic mass. Now, a couple things. This percent abundance idea is just how common this element is in nature. And of course, we have different isotopes of elements in nature, and these go into calculating average atomic mass. This is the reason why when we look on the periodic table, let's say at any given element, we'll pick an element here. Let's say we pick the element of lithium. Lithium has an average atomic mass of 6.94. Now, that decimal is telling us that there's something interesting going on. In the previous talk, just a couple minutes ago, I told you, that we would have 3 protons and 3 electrons given a neutral atom of lithium. And you might be thinking to yourself, wait a minute, how do we calculate the neutrons if we have a decimal here? Well, that decimal is representing the weighted averages and the percent abundance of different isotopes. So if we want to calculate this, most common way is just to round this value off to the closest whole number, which would be 7. And if we subtracted those two, we would get the number of neutrons as 4 in lithium, most common isotope of lithium. But let's jump into how to do these calculations. We cover these a little bit in general chemistry as well. So here's an example. We have chlorine 35, and chlorine 35, they're telling us that our percent abundance is 75.78. Okay, so chlorine 35, 75.78. So that's a pretty high percent abundance for an isotope. And I think I have a typo here. I do have a typo here. This should read chlorine 37 has a percent abundance of 24.22. Calculate the average atomic mass of chlorine. So we have 2 different isotopes, and they both have differing percent abundance. So just to take a look at this real quickly here, we're going to take our mass of chlorine 35. Now, if they give us the mass, like let's say they gave us 35.421 or something like that, we would go ahead and use that value. In this problem, they did not give us that, so we're just going to use 35. And we're going to take that mass and we're going to multiply it by its percent abundance. Whenever we multiply it, we have to turn it to a decimal, so we're going to slide the decimal place 2 places to the left or divide by 100. 75, 78, just like that, and that's our percent abundance. So we're going to multiply those two values together. Then we're going to add that to 37, the other isotope's mass, and its percent abundance. So 0.2422. Okay, and I'm going to run that through my calculator, come up with a value of 35.5 AMU, atomic mass units. And that's pretty good, pretty close. If I check it on the periodic table, chlorine has 35.45, which would round off to 35.5. So we're really in the ballpark on that calculation of the percent abundance. That is the end of today's AP Chemistry summer assignment number 4. Of course, there's going to be a quiz with this. And a worksheet that goes along with it as well. As always, if you have any questions, please feel free to email me or post those questions up in Classroom.